We are 1 month away from the final launch of a massive public web portal. Development is running smoothly, the servers are humming, and the finish line is in sight. Then the client sends a casual email. They want to add a third-party mileage point integration to the payment module. On the surface, it sounds like a simple request. The project manager wants to keep the client happy, so they accept the addition without a formal review. They type the new feature into a spreadsheet on their desktop, save it as Requirements version 2 Final, and pass it straight to the developers. But a spreadsheet cannot map logical dependencies. What no one realizes is that routing data to this third-party mileage system directly conflicts with the portal's core encryption architecture. Right before release, the system fails stress tests and catastrophically crashes. The resulting security vulnerabilities cause half a year of delays, mandatory weekend rework, and ultimately a multi-million-dollar lawsuit over unpaid labor. The International Requirements Engineering Board points out a harsh reality of software development. Changing requirements are a normal, inevitable part of engineering. They are an expected behavior, not an anomaly. The root cause of this project's collapse was the archaic method used to track the alteration. Managing a complex living system with static text documents guarantees critical information will slip through the cracks. To survive constant updates, engineering teams abandon text files and adopt specialized data-centric management tools. Here, each requirement is extracted from the page and treated as an independent, trackable object living within a unified database. When a project reaches a major milestone, a specific collection of these objects is officially approved and locked down. This creates a frozen perimeter, known as a baseline, a definitive reference point for the development team. If a client requests a modification to this baseline, we don't rewrite a massive specification manual. Instead, only the targeted object updates. Its content version increments to 2.0, while its status metadata shifts to change proposed. Separating the content version from the approval status prevents administrative gridlock. Fixing a minor typo updates the version number, but the status remains approved, sparing the team from an exhaustive reauthorization process. This visual compares two tracking methods, the manual nightmare of a spreadsheet matrix on the left and a dynamic traceability graph on the right. Linking individual requirement objects together generates this multi-layered network, establishing bidirectional traceability. The graph provides context in both directions. Moving upward, we track pre-requirement specification traceability. This isolates exactly where a specific feature originated, tracing its roots back to stakeholder interviews, business goals, or strict legal regulations. Moving downward maps post-requirements traceability. This shows how that exact same feature dictates specific software architecture choices, individual lines of source code, and the specific test cases required to verify it works. This traceability graph is an essential diagnostic map. It allows engineers to trace the entire physical and logical web of dependencies before they make a single alteration to the system. Consider a defense contractor building a military tactical communication system. Mid-project, the military sends an official request to update the encryption protocol to a newly released standard. This request is routed to a change control board. This is a multidisciplinary panel of architects and quality managers tasked with evaluating modifications to protect the system's technical integrity. This top-down graph demonstrates how the board runs an automated impact analysis. By selecting the top-level encryption requirement, they trigger a calculation that maps the exact blast radius of the proposed alteration down the chain. The software isolates the affected nodes and generates hard numbers. Updating this single protocol requires rewriting 50,000 lines of firmware, invalidates 200 integrated test cases, and will cost an additional $1.5 million while delaying deployment by 4 months. The board presents these exact figures to the military. Faced with the reality of the cost and delay, the military opts to defer the new encryption standard to a future phase, leaving the current system architecture secure and on schedule. Effective change management forces stakeholders to honestly weigh technical consequences against business value using objective data. Modern software development relies heavily on agile methodologies. Teams moving in rapid sprints cannot pause for formal control boards or massive document updates. In this environment, the product owner takes on the responsibility of a streamlined control board. They process incoming changes dynamically by evaluating and reprioritizing user stories within a constantly shifting product backlog. The necessary tracking is maintained through continuous traceability. A user story ticket is automatically linked directly to a developer's code commit, which instantly triggers the automated testing pipeline to verify the build. Agile methodologies do not abandon the need to trace dependencies. They simply bake that tracking directly into the background of the developer's daily workflow. By moving away from static files and adopting a data-centric approach to requirements engineering, organizations can handle endless client requests. They turn the chaos of constant updates into a predictable, controlled engine for innovation.